All right, let's do this. So we're talking about proportional segments in circles, and often this just kind of gets swept under the rug or used in such a way that you don't see the beauty behind it. So the big idea here is these three scenarios create similar triangles, okay? And I'm going to go over why. We'll set up the proportions ourselves. But basically, you just add a few lines. Those two triangles are similar. You add these two lines. Those two triangles are similar. You add these two lines, and those two triangles are similar. So that's what we're going to investigate right now and come up with some shortcuts that you can kind of copy down and reuse. Some things will come up, or quadratics will come up in this because you'll be multiplying like x times x plus 8. So we'll solve some of those problems together. So let's get into it, okay? The first one right here, the shortcut is piece plus piece, like on the same chord. So like this times this is always equal to this times this. And they don't have to intersect at the center. These are any two chords in a circle. That's pretty powerful, okay? So let's see why, all right? If I connect to this line here and this line here, well, what I get is two inscribed angles opening up to the same arc. And so I know those are congruent, right? I mean, if this was like a 40-degree arc, then both of these would be 20. They're both half of the same number, so they're both congruent to one another, okay? So we got those two are the same. And we also have vertical angles are the same, so these two are the same. And we have two inscribed angles opening up to this same arc over here. So this one, whoa, that's crazy. Come on, pen. And this one are congruent, okay? So now we've got two similar triangles. Let's set up a proportion. So we got A is 2, so that's between 2 and 3. That's the same thing as D, okay, in the other triangle. So A is to D as, and then C is, so I'm going from this smaller triangle to bigger here. So as C is to, and then its proportional side over here is B. Now if you just cross multiply, you get A times B equals C times D. And that's our shortcut up here, right? Is the two pieces of the segment, A and B, multiply together to be C plus D. So I'll erase some of my work here just to clean this up. But our shortcut we derive just from those similar triangles is A times B equals C times D in this picture. That is going to be so useful. By far the one you use the most out of this whole section, this whole chapter. Not chapter, section. All right, let's look at the next one. What about here? How do we get similar triangles? Well, again, I mean, there's really only a few points of intersection here that we could possibly connect. So I'm just going to connect a couple of those, all right? So I'm going to go here, because again, our super mega ultra theorem is inscribed angles. And look at this, we have angle and angle both opening up to the same arc, both being inscribed angles. So if they're both opening up to the same arc, those two angles are congruent. And this angle is congruent to itself. So we have this triangle here that's A and C plus D being similar to this triangle here that's A plus B and C, right? And so if those two are similar, let's set up a proportion. So going from this triangle to this triangle, I get A is to, and those are similar by AA, right? So A is to C as, and then C plus D is to A plus B. Now cross multiplying, I get A times A plus B equals C times C plus D. Now in the original picture, what that means is we have a piece of this times the whole thing, A times A plus B, is equal to C times C plus D. So it's the outside piece of that segment times the entire segment is equal for both of them. And so that's why I wrote here outside piece times the whole, right, along the same segment. So outside piece times the whole is equal to, and then in maybe pink here, I'll do outside piece to the whole of the other. So outside piece times the whole. So that product is equal. And again, this is going to save us a lot of time when we come into these scenarios with lengths in a triangle. Now, this case down here is really just the same as the last one, right? Because if we just did the same steps, we have this length, which is the outside portion, times the entire thing, which is the same thing, and we get WX times itself, because this one's just WX plus 0 is the entire thing. So really, I don't even know why this is a separate theorem. It's just a edge case of the first one. But let's look at it. So if we connect these two and these two, really it's the same connections we made last time, except these 2 points here have merged. So we just take this point, and as this black line moves up, they get closer and closer until they're one single point, and this is tangent. And so we're really just doing the exact same thing, right? But here's the trick. Now, this is an inscribed angle of this arc, and so is this. It's harder to see, right? But this one is, when we have a tangent to a circle, it does act as an inscribed angle of this arc. And so if this arc is x, then that angle in there is 1/2 of x. That's still true. That one's harder to see for people. And then, of course, both triangles share this angle. So let's redraw it. We have this big triangle like this that has this angle and this angle. This whole side is a plus b, and this side is c. And that's similar to this triangle is kind of upside down and backwards here. That's c and b with a double and a single. And so let's just set up the proportion, right? So going from this one to this one, that is c is to b as a plus b is to c. Cross multiply, and we get c squared equals b times a plus b. Or in other words, I'm going to use different color, piece plus whole, so c times itself, and then is equal to b times the whole a plus b. So it's really the same thing as before. So outside piece times whole, except here the whole is the outside piece plus 0, or just the outside piece again. All right, so just to summarize, here's our 3 shortcuts in one screen, okay? You could just copy them down in your notebook, pause here, time warp. Okay, we're going forward. We're solving now. All right, so first off, we come across a problem. And, oh no, somebody made a mistake. Well, let's see here. This is the outside piece times whole, and outside piece times whole. So this is 3 times 3, because the whole is still just the 3, equals the outside portion x times x plus 8. So that's what we should get. Let's look over here. Oh, they used the inner piece. So they mixed up the 2 shortcuts, where they did the one where you do piece times piece equals piece times piece. They mixed that one up with the scenario like this, where it's piece times whole. They mixed that up. Whereas Letitia over here got it right. That was the right setup. And then they had to do a quadratic. Ooh, I'm getting ready. All right, let's see. Ooh. Okay, first ones. No quadratics here. We're just setting this up. Oh, I know with this shortcut, piece times piece along the same segment, so x times 9 equals, and then maybe in a different color, piece times piece along the same segment, so 3 times 6. And so we get 9x equals 18, x equals 2. Great. Okay, next one. This is the outside piece times whole thing, 20 plus x, equals the outside piece 31 times the whole piece, which is again 31. So we get, 400 plus 20x equals whatever 31 squared is. So 20x equals 31 squared minus 400. Whoa. And then we divide by 20. So x equals 31 squared minus 400, all divided by 20. Have fun with that one. All right, the other one over here. We've got, okay, so this is one of those outside, so it's outside piece times whole. So we get x times x plus 10, good golly, equals 3 times, and you add the 3 and the 5 together to get 8. So we get x squared plus 10x equals 24. It's almost like at the end of geometry, we're trying to get you ready for Algebra 2. This is kooky. There must be some like deeper meaning, deeper reason why they do this. All right, so let's subtract all to one side. That's how we solve it. So we get x squared plus 10x minus 24 equals 0. We want to factor this. Now remember, I use the Xbox method, so I want something that multiplies to make, so I multiply the a times the c, and so this times this, I get negative 24, and I just put the b on bottom, so the positive 10. And I'm looking for something that multiplies to make that top number and adds to make the bottom. So I know just by quick guess and check, I could come up with positive 12 and negative 2. Those satisfy, right? Then I go over and I go, well, that was my x. My box here, maybe I'll zoom in so we have more room. I always put my first term unchanged in the top left. That was positive 1x squared, and unchanged my last term here. Then what I'm doing is I'm putting those other 2 terms we found in these other 2 boxes. We go, ooh, we split up that middle term that used to be plus 10x to plus 12x and minus 2x. That was the whole reason for the x part. Okay, and now we're done. Now we're just going to go factor out each column. So in the first column, we could factor out a positive 1x. In the second column, we could factor out a positive 12. The sign always matches the first box in the x box method. And then over here, we could, on the top row, we could factor out again just a positive 1x. And on the bottom, we pull out that negative, and so we get a negative 2. Just checking, negative 2 times 1x, yup. We go negative 2 times positive 12, yup. So all of these should multiply correctly. Positive 12 times this, so everything works out. So our factored version down here after the xbox method is we get x minus 2 times x plus 12 equals 0. And then we go, well, the only way two things can multiply to make 0 is if x minus 2 is 0 or x plus 12 is 0. So either x is 2 or x is negative 12. And then we go back to the problem and say, well, could x be 2? Yeah, sure, that works. Like we could plug it in and double check if that works. So is 2 times 12 equal to 3 times 8? Yeah, 24 equals 24. Check. Can x be negative 12? So could we have a negative side length here? No, we could not. So that was not a valid solution. But x can be 2 is a valid solution. Sometimes both are valid, sometimes neither are valid. The key is you go back and check, is the segment, like maybe the segment was x plus 20. Well, then both would work, right? This makes the segment 22, and this makes the segment 8. So it doesn't matter if the variable is negative. What matters is that the segment has a negative length. Okay, let's delete that. Ka-chow. All right, let's go to another one. Ooh, quadratic, spooky. So this one is piece times piece. And so we got x times x plus 8 equals 5 times 4. So we get x squared plus 8x equals 20. So x squared plus 8x, moving it all to one side, equals 0. I'm going to use my xbox method. So I get it multiplies to make negative 20, adds to make 8. That's positive 10 and a negative 2, right? Double checking, yes. Then I put my unchanged first and last term. So first term, last term. And then I put my 8x split. So now I have 10x and negative 2x. And so now I can factor. So I get an x, whoa, not x squared, an x out of that column, a 10 out of this column, an x out of this column, and a negative 2 out of this column. Double checking, those all multiply correctly. So this was x minus 2 times x plus 10 equals 0. So either x minus 2 is 0 or x plus 10 was 0. So x is 2 or x is negative 10. Let's go back and go, well, we cannot have, whoa, that's not an eraser. We cannot have a negative 10 in there because that makes both this length and this length negative. So it worked out that negative times negative, the formula worked, but we can't have real segments having negative lengths. But if we plug in 2, we get this is the length of 10 and this is the length of 2, which does multiply to get 20 just like this. So that one checks out. This one does not. Okay, let's do a couple more. Here we get what looks like a quadratic. So we get outside piece times whole. So that's x times x equaled outside piece times whole. That's 3 times 12. And so we get x squared equals 36. But we don't need to solve this like a quadratic because we don't have two terms with an x in it. We only have one term with an x, so we can just isolate that. We already did. So now square root both sides, x equals plus or minus 6. And then plugging it back in can't be negative, so we get the answer is just x equals 6 because we checked both. All right, same thing over here. So we get piece. So let's do piece. Outside piece times whole is 4 times 4. Outside piece times whole is equal to 2 times 2 plus x. And so we get 16 equals 4 plus 2x. And so we can just solve. That's 12 equals 2x. That's x equals 6. We can go back and double check that really quick. Let's see. 4 times 4 would be 16. And 2 times 8, because this would be 6, would be 16. So that checks out. Okay. Whoa, let's zoom out. Whoa, this one's scary. Outside piece times whole. That's x squared plus, nope, that's silly. I shouldn't do that all at once. Okay, x times x plus 16. What? Because we have to do the whole thing. We have to add those two together. equals the outside piece times the whole thing. So we get x, yeah, let's combine it first. So we get 2x plus 16. So we get 2x squared, because they distribute this to the 2x. Then we distribute it to here, plus 16x, equals 256. Moving it all to one side. So a step that I haven't brought up yet, but that comes in handy now, is whenever we have a lead coefficient of something other than 1, we should absolutely take out the GCF. So if this isn't an equation, we have to just factor it out. But since it's an equation, we could just divide both sides by 2, because we can divide both sides of an equation by 2. That doesn't break anything. So we get x squared plus 8x minus 128 equals 0 is the real equation there. Once we get out, there was an extra 2 in everything. All right, so now again, we're going to use our x box. So first times last. And then the inner one. Now this is a big number. So what I do then is I go like this. Well, I know they multiply to make a negative. So 1 is negative, 1 is positive, right? And then I list my possibilities. Well, it's 1 times 128. Nope. 2 times 64. Nope. 3 times doesn't work. 4 times, ooh, what's 4 times? 32. Okay. Ooh, we're getting closer. Okay. 5 times doesn't work. 6 times doesn't work. 7 times doesn't work. 8 times, what is it? 8 times 16, I think. The reason I know that is this is all made of 2's. If you factored this, this is like 2 to the 7th power. So I know the only things they're going to divide are 1, 2, 4, 8, 16, and so on. So that's 80 and 48, which does add up. And look at that. Those were the numbers we were looking for. So we know that we had the positive 16 and the negative 8. And you could just use a calculator to help you with this. You just literally go 128 divided by 3. Didn't work. Came out to a decimal. 128 divided by 4. Hey, it came out to be 32. 128 divided by 5. 128 divided by 6. You can just try every single combination. And there we go. We just did it. So now we get first unchanged, last unchanged. And then we split it into a positive 16x and a negative 8x. Some people like to have the x's involved over here. I don't really care either way, but that works for you. Whoops, and there. Okay, and then we're going to factor out the GCF, so we get an x. We get, this has a 16. This has just an x. This has a negative 8, and everything checks out. So factored, we have x minus 8 times x plus 16 equals 0. So we either have x minus 8 equals 0 or x plus 16 equals 0. It's the only way that two things could multiply to make 0. So either x is 8 or x is negative 16. So let's look at the scenario. So if x is negative 16, that means we have 0 times negative 16. That's a little crazy. Oh no, we'd have negative 16 plus 0. So negative 16 times the whole thing, negative 16. So it would have worked out, but we cannot have segment lengths of 0 and negative 16. That's crazy town. But if we plug in 8, we get 8 and 24. And so 8 times 32 is the same as 16 times 16. So this was our answer there. All right. Let's do, whoa, 2 more. This is crazy. And then I actually have like a couple more interesting scenarios. So I'm going to do a couple more problems for sure. So this one, we have the same segment here and here. So outer piece times the whole and outer piece times the whole. The only way we can have the same value here, the same value here, is if these are the same. So just x equals 5. That's done. I just wanted to see it so you could see that we do that, right? Because if we literally, like, whatever this was, right? Let's say it was 9, 9, x, and 4, right? We're going to literally have x times x plus 9 equals 4 times 4 plus 9. The only way that can be true is if those values are the same. So, all right, I just want to show you that. Okay. Anyways, let's go on to the next one. Let's see. So we got outside times whole, outside times whole. So we got x times, and then 3x plus x is 4x equals outside piece times, whoa, I wrote it wrong, 8 plus x plus 2. Okay, so this is 4x squared equals 64 plus, oh, I should actually make this x plus 10 first. So this was x plus 10. We distribute the 8 into x plus 10, and we get 8x plus 80. Moving it all to one side, 4x squared minus 8x minus 80 equals 0. Again, let's just divide by that common factor of 4. So now we get x squared minus 2x minus 20 equals 0. Much easier. So multiplies to negative 20, adds to negative 2. So that would be, is that going to work out? We got 1 times 20, we got 2 times 10, we got 3 doesn't work, we got 4 times 5. There's nothing that makes a negative 2. Did I do something wrong? Just double checking my work. Otherwise, we're just going to use the quadratic formula here to get a sloppy number. Yeah, I think this works. Okay, so if we can't factor it, right, and we know we can't factor it because one of these has to be negative, one has to be positive, so when we add them, it subtracts. And this has a difference of 1. This is 8, and this is 19. So there's no nice number that makes this true. So then we just plug it in the formula. So x is negative b plus or minus the square root b squared minus 2 minus 4ac, haven't done that in a while, all over 2a. So we just plug it into the formula. So this is negative 2, that's b, plus or minus the square root of negative 2 squared, minus 4, a is just 1, c is negative 20, and that's all over 2 times 1. So that's 2 plus or minus the square root of, and up here I'm just going to do it in a different color really quick. So that's 4 minus, and then the minus and the minus cancel out, so we get plus 80. So we get the square root of 84, which we could simplify a little bit, all over 2. So square root of 84 is square root of 4 times square root of 21. Or in other words, 2 root 21. So we have 2 plus or minus 2 root 21 over 2. So we can divide everything on top by 2. So x is equal to 1 plus or minus the square root of 21. And looking up here, x is a side length, right? So x has to be positive. And so down here, we can't have 1 minus the square root of 21. Square root of 21 is around 4 point something, right? Because square root of 16 is 4, square root of 25 is 5. So we can't do 1 minus 4.5. That would be a negative. So we get rid of that negative, and there's our answer. 1 plus square root of 21. I just even looked at the answer in there. Yeah, that is the answer. They approximate it to 5.6 because that was about what we got, 1 plus 4.5-ish. You just have to punch that in a calculator and see what the square root of 21 is. All right, so knobs. If you remove a knob from a kitchen appliance, you might notice that the hole is not round. It's got this flat portion on the circle. Now, suppose the flat edge is 4 millimeters long. So we've got a circle. Okay, whoa. We got a circle. Let's make it a perfect circle. That was a terrible perfect circle. We got a perfect circle. And then we got this flat part that's 4 long, okay? Here's 4 long. And then the distance from the curved edge, so distance is perpendicular, is 4.25 centimeters long. Oh, wait. The distance from, they mean the other way. They mean the big side. Silly me. Shoo-ba-doo. So this distance is 4.25 long, okay? Yep. Find the radius of the circle containing the hole. Well, something you got to remember, that this distance, this is symmetrical down the middle. This distance then cuts the chord into 2 symmetric parts, right? So this is 2 and 2. And yeah, this is the radius here. And then this would be some distance. And this would be just the radius minus the distance. But we don't care right now. We can just figure out, given the 4.25, what the missing piece is. So let's find the missing piece first, and then we'll use that to find the radius, okay? So we got 4.25 times x, right? Piece times piece equals piece times piece equals 2 times 2. So we got 4.25x equals 4. I'm going to multiply both sides by 4 just to get rid of the decimal. So we go times 4 times 4. So we get 17. X equals 16. Whoa, that's cool. So x equals 16/17. Okay, I'll backtrack because I made a tiny mistake in my arithmetic. So here we are. So now that you have 16/17, you just go this entire length. Whoa, I'm drawing with my eraser, not my pencil. this entire length, 4.25 plus 16/17, is the diameter, right? And right here it says find the radius. So then you just divide that by 2. So whatever that comes out to be, right? So we could rewrite this as 17/16, and then become some cool fractions. 17/16 plus 16/17. Whoa. All divided by 2, which is fun. But you could also just plug it into the calculator. You get this is around 5.2 divided by 2, so you get around 2.6 as your radius. You just have to actually do some arithmetic there. Oh, it's not 17/16. That was my mistake last time. 17/4. That was why I made the mistake last time. All right. Anyways, whew, good problem. All right, let's do another one here. So this one, you go, okay, we're finding each variable, but we don't have this. But we do know the radius is 8. So what's that last expression? This is 8 minus x. And then it's just straightforward after that, right? So then it's just 8 minus x times x plus 8 equals 9 times 4, just piece times piece, right? But now remember difference of squares? This turns out to be x squared minus 64, because what you get is, if you distribute and distribute, you end up getting 8x plus 64 minus x squared minus 8x, and those minus 8x and plus 8x cancel out, or you just remember that a times b, or a minus b times a plus b, always works out to be a squared minus b squared. It's called the difference of squares. Equals 36. Adding the 64, we get x squared equals 100. So x equals plus or minus 10. Again, it's an actual side length, so we only use the positive value there. All right, this other one, you have to remember that radius or diameter, so something passing through the center that makes a right angle, symmetrically cuts this in half. So this is y. You have to remember your chord properties there. And then again, it's just piece times piece. So 2 times 5 equals y times y. Another way to do this is by drawing a right triangle here and going the radius is 5. What's this distance? Well, that's 5 minus 2, which is 3. And then you could use Pythagorean Theorem here. Oh, and look at what you get. In that case, you get, right? We get y is 4. How do we not get that here? Oh, because I forgot to do piece times piece, right? Classic me. Look at that. Good thing I did that an alternate way. We know we should get 4. It's piece times piece. What's this piece? This piece isn't 5 long. It's 5 is the radius, plus from the center to that other spot is 3, because this has to total 5 also. So it's 2 times 8. I'm just moving too quickly. 16 equals y squared. So y equals plus or minus 4. In this case, it has to be positive because it's a side length. So y is 4. Woo, good thing we caught our own mistake by doing it 2 different ways. All right, over here on the next one, we've got, look at this. We've got this times this equals this times this. So we got 2 times x equals 3 times y. That's 2 variables, 1 equation. So another thing we could write, though, is we could say, well, if they went through the center, we could say, like, well, diameter equals diameter. But these are just 2 random chords, so we can't say that. But look at this. We have another relationship here. Remember that one? Outside piece times whole. So 12 times 12 equals outside piece times whole. So this one, whoa, I circled the 2, but the 2's not part of that. Outside piece times whole. So that would be 6 times, and the whole would be 6 plus y plus 3. And so this equation would be 144 equals, this would become y plus 9, and then we distribute it in, we get 6y plus 54 minus 54, and we get 6y equals 90. And then we divide by 6, and we get y equals 15. Now we go back and plug it into our first equation, and we get, whoops, we don't have a lot of room. We get 2x equals 3 times 15, or 2x equals 45, or x equals 22.5. All right, let's do another one. What? This one's freaking crazy town. So let's only look at this relationship first. So we go, oh, outside times whole, 10 times 18, equals outside times whole, CS squared. And then go, okay, well, now we use that up. We know nothing. Now let's do the other one. So over here, we get outside times whole. So 9 times 9 plus x equals, and then outside times whole, cs squared. So two separate relationships in two separate circles. But now look at what we can do. They're both equal to cs squared. So that means we get 10 times 18 equals 9 times 9 plus x. And then it's just a good old quadratic. So we get that, and that's 81 plus, it's not even a quadratic. What am I talking about? Plus 9x. Subtracting, we get 99 equals 9x. So x equals 11. And we could go back and plug that in, okay? So let's go over to the next one. What the heck? Look at all this. So we got outside times whole, which only goes to here, not whole going out of the circle. So this relationship. And then outside times outside. So here we get x times x plus, 24 equals 9 squared. Okay, and then separate relationship, if we just erase all that, a separate relationship is outside times whole equals outside times whole. So we get 2x times 2x plus 24. Yep, okay, equals y times y plus 12.25. Okay, so we can't solve this yet because it's two variables in one equation, but we can solve the top one. So let's do it. Let's do it. Let's slide this down. So we get x squared plus 24x equals 81. Let's subtract. X squared plus 24x minus 81 equals 0. Let's Xbox method that. So I know we'll have an x squared and a minus 81 here. So up top we get a times c. On bottom we get b. Now it's a big number, so we just go, okay, well we know one's negative and we know one's positive, and they add up to a positive. So let's see, is it 1 times 81? Nope. 2 doesn't work. 3 times 27? Hey, we already got it. So we just put in, that's a positive 27 and a minus 3. So that ends up with a plus 27x and a minus 3x. And then factoring out, we get these have an x in common in this row. And then we go, these have a positive 9, I think, in common. These have an x. No, 27 goes into both of those. Because 81 is 27 times 3. So this is, they have a 27 in common. I knew that because the x times something had to be 27. And so that's how I back-checked myself. Okay, this one keeps the sign of the outside thing, so minus 3. And look, those work. Those work. So everything's multiplying correctly now. That's what I wanted to see. And so this ends up being x minus 3 times x plus 27 equals 0. So either x minus 3 is 0, so x is 3. Or x plus 27 is 0, so x is negative 27. We go up top, and we go, well, x couldn't be negative 27, because it's an actual side length here. So plugging it in, we get this is a 3. This is a 6. Okay. And then we could check 3 times 27 is 9 times 9, 81. Yep, it worked out there. Okay, so now we could plug it into the next one and go, this was just saying 6 times whole thing, 6 plus 6 times 30. Right? That was 6 times whole thing. So 6 times 30 equals y times that. And so then we just get 180 equals, and we distribute that in, y squared plus 12.25y. I'm going to multiply by 4, so we get 720 equals 4y squared plus, what's that, 49? Okay, y. You could have just used the quadratic formula, but I don't like to. So moving everything to one side, we get 0 equals 4y squared plus 49y minus 720. And now you're going to try and figure out something for the Xbox method. So this is our first big challenging one. Ooh, okay. So first term, 4y squared. Last term, minus 720. Up over here, a times c. This is freaking crazy town. We're getting negative 14. No, we get 4 times. That's 2,880. That's crazy. And on bottom, we get it adds to 49. Okay, so we need two numbers that are about 49 apart. Okay, so you could just start checking anything. 1 times 2, 8, 8. I know that's not going to get it done. That is way too far apart. So I could jump, and I could be like, well, 10 times 288. Whoops. makes that. I go, ooh, I'm getting closer, right? Those are 268 apart. So let's try 20 times, and now it's 20 times 144. Hey, we're getting even closer. That's, 124 apart. So now let's try 40. So 40 times, and that would be, I just know I cut the other thing in half, so that's a 72. So we're 32, so it's somewhere between those. So let's try, I don't know, 36. I'm using a calculator for this. So we go 2880 divided by 36. And that's 80, so that's 36 times 80. And is that right? So that's 44 apart. Gosh darn, is this not gonna work? Okay, so let's try 35, maybe that, 2880 divided by 35. And that didn't work. 2880 divided by 34. 2880 divided by 33. 2880 divided by 32. Okay, that's it. So we got 32 and 90, and those are 50 something apart. So it doesn't work. So there is no clean solution here. That's so sad. Then you just punch it into the meat grinder of the quadratic formula. So negative b plus or minus square root b squared minus 4ac all over 2a. And it's just a calculator. That was no fun of an ending. All right, I'll leave that to you guys to plug in. Woo! Hope you enjoyed the video.